Oh, I'm live ready. Okay. Sorry. I was trying to get some stuff set up, and apparently YouTube just wanted to send me right into being live. Well, very cool. Let me see if you can see me. Trying to adjust some things a little more before I begin, but make this a little bit. Sorry, whoever just joined, I am adjusting my camera so you can actually see what's happening. It's unfortunate. That might work. Sure. Can't really see this. Now it's daytime out. Anything else? Nah, the problem is you really can't see this screen. That sucks. Okay. Basically, you are not going to be able to see the screen right now, sadly. But I'm just going to go through some problems on Revision Village. I will actually pull them up here. I will make sure I'm not accidentally doxing myself, which would be very cool. So, HL Chemistry. Here we go. This is what I'm doing. These are the problems. Let's go ahead and let me just live stream. There we go. Okay. So question's going to be on the left. My working is going to be on the right. That's essentially what's going to be happening. Okay. Let's hop straight into it. Now that I think this is somewhat of a suitable setup. Okay, which statement about electrochemical cells is not correct? The reaction of voltaic cell. Let me also pull up some notes for it. MSG Chem. I'm going to be covering topic 9 and 19. Okay. There we go. Electrolytic cell is non-spontaneous. An electrolytic cell. Okay. So if I'm not mistaken, is it the voltaic cell? Okay, I'm trying to review my weakness right now, which is this topic. Anode is negative in voltaic cells. So for voltaic, so that means electrolytic, it would be C, correct? Because electrolytic is pretty much cathode's the negative, yeah. Yeah, C. KNAP. I mean CNAP. CNAP. So what does that mean? Cathode negative. Anode positive. That's for electrolytic cells. Okay. So then that would be C. This would be a nice one to read just because it's the difference between electrolytic and voltaic, which is a good distinction to make because electrolytic has the battery and the voltaic is just your standard half cells. Half cells connected by a salt bridge. Which row, indicated by the table below, contains the correct electrolysis of, okay, zinc chloride, right? Okay, let's make a tiny diagram. So electrolysis, let's refer back to the electrolysis diagram back here. Okay. So I'm gonna have it like this, go up, down. It's gonna be our cathode. It's gonna be our anode. Okay. So flow of electrons is gonna go up here. Electrons, battery. Such a crap drawing. And you add the battery. There we go. Battery. Then oxidation occurs at the anode, okay, and reduction occurs at the cathode. Oxidation. So which species is going to be oxidized? Which one's going to be? Okay. Yeah, this really is my weakness. So let's think about it. What can be produced? Zinc 2 plus can be chlorine gas produced. So essentially, we're going to have this. So this is going to be attracted to that. So the anode's going to be okay, makes sense. Okay, so this is going to be our positive, so it's going to attract our chlorine. This one's going to be our negative. This is going to attract our... I need to decrease my pen size. This diagram probably makes no sense, but essentially chlorine atoms, or chlorine anions are going to be attracted to anode and are formed chlorine gas once they get stripped of their positive charge, if I'm not mistaken. And that's going to force it into the cathode, where the zinc 2 plus are going to just become solid zinc. So what we're going to get is we're going to get chlorine gas and we're going to get zinc. This is going to be our oxidized. This is going to be our reduced. This is going to be undergo oxidation. Chlorine gas is going to go, chlorine anion is going to undergo oxidation. The zinc solid will undergo reduction. So, which answer does that match with? So we found anode, we're going to get chlorine gas. Cathode, solid zinc. A. Yep. Cool. Let's look at their explanation briefly. That's going to gain, it's going to get reduced. Yeah. Okay. So pretty much the aqueous ions are going to gain and become solid zinc and chlorine gas. Cool. Makes sense. Let's go on to question 4. So what do we have here? What statements are correct about the electrolysis of aluminum oxide? So aluminum oxide should be that, right? If I'm not mistaken. But that really doesn't matter. So aluminum ions are going to gain, yes, oxide ions lose electrons. Hold up. Electrolysis. Hold up. So, anode is the one where they get stripped of that electron. And it's going to force it into the cathode. So the cathode is the site of reduction in an electrolytic cell. So 3 is correct. About 1 and 2. Okay. We already know number 2 is going to be wrong because we know that the oxide ions are going to go towards the anode and get stripped of their, or wait. Yeah. Get stripped of their electrons, right? At the anode. And then the aluminum ions are going to gain the electrons at the cathode. Right? So from what I'm thinking, it would be B. Yeah. Oh, nice. Okay. They keep giving you nice mnemonics to know. Cathode reduction, oxidation at the anode. So that's for electrolytic cells. Nice mnemonic. Reduction is gain of electrons. Yeah. Okay. Moving on. So we're gonna have question 5 now. Question 5. Oxygen and water are produced. Nitric acid. Okay, then we're given some equation. So define reduction in terms of electron transfer. So definitions. So reduction is when the aqueous cation gains electrons to achieve a quote-unquote neutral state. That's what I would say for the first one, just because that's what the first thing that pops into my head. I'm not saying it's correct. We'll double check though. State. Okay, so K MnO4. Okay. And then yada yada becomes 4KNO3. No, sorry. I'm supposed to be looking at MnNO3 2. Okay. So oxidation here should be +7, right? then here it should look like that's looking like +4. No, I think that's +2. Because according to, yeah, it's looking more like +2. We'll double check this. But identify which has been oxidized in this reaction. Okay, so which one? Okay. So oxidized. Okay, so oxidized means it underwent reduction, right? So, and then wasn't it a change? Okay. Ooh, oxygen has been oxidized. Oops. Okay. So oxygen has been oxidized. Yeah, I see that because it goes from negative to 0. Yeah. Yeah. Okay. My bad. From, what was it? HNO3 to 0 and cool. Okay. The diagram shows voltaic cell. Okay. So they tell us that this is reduced, this is oxidized. And this is a voltaic cell, meaning that at the cathode it'll have a positive charge, if I'm not mistaken. So we already know this one okay. So we know magnesium strips oxidized. Now I just need to determine whether it's at the anode or the My exams are in what, May? They begin in May. Don't they begin in May for everyone? Right? So it's anode, so it's gonna So considering the fact that it's oxidized, it will be at the anode, correct? Yeah, B, anode. Cool. I'll write the answer down to remember that I did it. B, at the anode. Nice. Yeah, because it loses electrons, takes place at the anode. Let me just write that down. Oh, nice. Okay, that's cool. Really good process that happens in any cell. My handwriting is actually chicken scratch. Question 7. An external power supply is used to drive a non-spontaneous process. Okay. I already know 1, 2, 3. This is according to Croa. 2 is correct. Oxidation does occur at the anode because the anode is positive in this case because it's an electrolytic cell. The cell could be used to extract the reactive metal from its molten salt. Yeah, I believe so. And then the non-spontaneous process. Yeah, I believe so. I believe all 3 are correct. I say D. Yeah. Because the introduction of the battery made sure that you're able to strip off those electrons because you're doing work to those electrons. And the reason why electrolytic cells are used, because if you have a non-spontaneous process that you want to occur, then you're going to add work to strip those electrons and make sure that actually does happen. And positive electrode is the anode, because according to Croa, this says cathode reduction. So at the cathode, reduction occurs and oxidation occurs at the anode. This is better to memorize than, cathode's positive. No, don't memorize it that way. Memorize the Croa if you're going to memorize. And then the aqueous metal ion is reduced at the cathode to produce the solid metal. Yes, because the cathode is negative in this case. And that's what happens. The aqueous metal ions are going to be attracted to the electrode, which in this case is the cathode. Well, the negative electrode is going to be the cathode, and it's going to be attracted to that, and it's going to form, whenever that happens, it's going to form its normal element, like in the example shown here. I'll show you this again. Like, see how this is being, the anions are being attracted to the anode. This is going to form chlorine gas, and the sodium here, you're going to see the formation of sodium. So that's how you have, like, from this molten salt, you're going to be able to form its own elements. So this, you're going to see some probably, green gas forming and going up to the surface, and you're going to be the formation of this, probably some bubbling maybe. Here you're going to see the formation of some like residue on this electrode. So that's what's pretty much just going to be happening. And the residue that you're observing is going to be the sodium metal. Okay, cool. Hold up. I need to text my father because he asked me if I wanted anything from a grocery store. Okay. Continue on. Sorry, quick break. Had to text him quickly. Okay, what happens to that when it's converted to this? Okay, so what we observe right here is we observe the 3 plus going to a 7 plus because we know it's this polyatomic ion has a negative charge, which tells us we know oxygen is going to have a charge or an oxidation state of -2. So that makes, and we have 4 of them, so that's essentially going to be a -8, but then that's not, okay, just a -8 overall, and then this is going to be, so -8, what plus -8 is going to give us -1, so +7. So from the 3 to a +7, we can tell that the oxidation number increases. So here, A, D are gone. And whenever it increases, it goes oxidation. So B. Question 8, B. Cool. Moving on. Question 9. Right? So which one is the reducing agent, right? Well, how I like to start off these questions is I always like to go Leo, Ger, then I like to add RA and OA. It's the ends of them. So which one is going to undergo oxidation? And because what this says is it says loss of electrons is oxidation, and that's the reducing agent. And then this says gain of electrons is reduction, and this is the oxidation agent. But we care about the reducing agent, so we want to see which one's oxidized. So which one is oxidizing here? We observe that Zn gets a higher number, so it's looking like Zn already. Let's double check with the other ones. Yeah. Zinc. Zinc 2 plus, or which one does it have to be? It has to be A because the Zn is going to form the Zn2 plus. So I'm saying A. Yeah. A. Cool. See, reducing agents are substances that oxidized. Yeah. The state of oxidation state of nitrogen on decreases. Yeah. Okay. Yep. Nice. So now moving on to question 10. Which compound contains 2 different elements with identical oxidation states? So just from looking at it right now, I would say B. Why? A, magnesium, if I'm not mistaken, that's first group, meaning that it's always going to have +1. That's not going to be the same as sulfur. And bang, that A's are already out because, yeah, we need something that's going to add up to -8. That's not happening. This hydrogen here, we're used to hydrogen being yeah, like this. So this is going to be +1, bromine +1, right? -2. Here, +1, +5, no. Here, +2, +4, no. B. Yeah, see, +1, +1 adds up to -2. Cool. Moving on. So we have an electrolytic cell. Nice. At which electrode will bromine form? And what is the process taking place there? Okay, so we're going to start off with our CROA. CROA. This always reminds us, at the cathode, it's going to undergo reduction, oxidation at the anode. So we have RS, so those are just our electrodes. DC power supply. So it looks like they inverted the battery on us. So it's looking like the flow of electrons is actually going to go this way towards R because they flipped around the battery. You see how it's the positive terminal over here and the negative terminal over here? Normally it's the positive terminals on the left side, negative terminals on the right side. So what they're trying to do, I think, is play a trick on you and flip it. So what will happen is the flow of electrons will end up going towards R. So this is going to look like our cathode. S is going to be our anode. So we want bromine to undergo oxidation, if I'm not mistaken, because it'll be attracted to the anode, right? And it'll form, okay. Okay. Because it's going to be Br minus, and this is going to be the Pb2 plus. So this is going to want to be attracted to the cathode. Br minus is going to want to be attracted to the anode. So we're going to see oxidation occur. So we're going to want to see it oxidize. We'll just start with that fact. So we already know it's going to be B or D. And then because they flipped the battery on us, the flow of electrons is this way, so we know this is our cathode, this is our anode. So it's going to be attracted to our anode, and I'm saying it's going to be B. Yeah. B. Cool. See? Because typically, like, you don't want to memorize the side that the anode or cathode is going to be on, because then they can do tricky stuff like this, because they're catching the kids off guard that memorized it, and they don't know what they're doing because they just memorized it. So they just did a simple thing. All they did was flip the battery and change the sides that the terminals are on. And if you memorize a diagram like this, like I showed previously, where the positive terminals over here on the left side and the negative terminals on this side, then you're gonna mess up the question. You're not gonna go which electrode it is. So essentially, what it is you're gonna have the flow of electrons go from the positive to the negative terminal. If you take physics, you should know that. So, yeah. Question 12. Man, I'm getting kind of hungry. Might take a break soon. Okay, a Daniell cell. Nice. Okay. So if zinc is more reactive than copper, so we know it's higher on the reactivity series. So zinc more reactive. I'm just going to write that down. When the spontaneous reaction occurs, which statement about the Daniell cell is correct? So, this is where I'm going to need to review my activity series and stuff. Okay. So spontaneity is going to be determined by, see how we know it's a voltaic cell, right? We have our voltmeter here, and we have our salt bridge. Yeah. And in order for it to be a spontaneous reaction, we're going to want it to be, if I'm not mistaken, a positive reading on your voltmeter. So what we're going to do is do this. This is your simple formula right here. Your cell is going to be the one undergoing, it's equal to the voltmeter reading of the one being reduced minus the one being oxidized. You get this from you can get these from your activity series. And how I like to memorize this, if I'm not mistaken, this isn't in your data booklet, but the cool thing about this is that the reduced minus oxidized, right? It literally spells redox. 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 It's literally the name of the unit, so that's how I remember it. Like that's how you get the voltage reading to be positive. So essentially, we're gonna want the one higher on the activity series to be the one being oxidized, so we can get a positive value, because the higher one on the reactivity series is going to be a higher negative number. So what we're going to want that to be is, obviously we want it to be a positive number. So because it's negative, we're going to plug it in here and we're going to get a positive number, because negative and negatives makes positive. And then we're going to have our reduced one here. So if we know zinc, we don't even need the activity series for this. So our zinc is more reactive than copper. So we're going to want to plug our zinc. Zinc is being oxidized. So we know our zinc's being oxidized. Why? Because it's more reactive. We want our more reactive one to be oxidized. And then reduction, copper. Cool. So what will we see? The mass of the copper electrode will decrease, or the flow of the electrons from the zinc to from the copper to the zinc electrode while the cell is operating. The blue color of the copper sulfate will fade over time, and the zinc electrode is a cathode of the cell. So we know zinc's not going to be. So let's write this down. How I like to always write it down is, if you're not sure on a multiple choice question, I always like to write down A, B, C, D like this in this order. And I always like to cross off the ones I just know aren't right. Like zinc, according to CROA, cathode reduction. We want our zinc to be oxidized, right? So D out of the way. C, I believe C is still a viable option. D, from the copper electrode to the zinc electrode, no. We want our flow to be from the one being oxidized, the one being reduced. So we're going to want it from the zinc to the copper electrode, right? Because this is the zinc's getting stripped of its electrons, and the copper is going to gain those electrons. So the B is wrong. That just doesn't make sense. Mass of the copper electrode will decrease. No, that goes against the entire fact that you're going to want your copper to be reduced. So what's going to happen is you're going to observe those copper cations be attracted to the copper electrode, right? We're going to see them being attracted to the copper electrode, and what happens is you're going to see the copper sort of residue forming on the electrode, meaning that the mass of the electrode will actually increase. So what we'll actually observe is from here, from the copper sulfate solution, we're going to see the blue start to fade, because the copper is going to form that residue on the copper electrode. So I say C. C. More reactive metals are more likely to lose electrons, be oxidized, and so zinc will lose electrons to form xenon 2+. Yes. Copper 2+ will gain electrons, forming copper, leading to a decrease in copper 2 concentration and the paler blue color of the solution. Yes. Electrons flow from the anode to the cathode. Yes. So what you're going to want to do is write down, also maybe mentally note the electron flow from anode to cathode. Cool. So now we're on question 13. That's done. So we have a Daniel cell again, right? Hold up. I need to make sure my dad doesn't interrupt. Okay, I am back. My dad bought some snacks quickly so I could keep going on with the stream. Oh, Pringles. Nice. Okay, so Daniel cell, this is pretty much very similar to the last question, if I'm not mistaken. Zinc, more reactive than copper. Yes, we know that. So the positive and... Okay, so two salt bridge options here. A, B are about the salt bridge. We're going to want to balance... What the salt bridge does, it balances out the charge of the cell. So we'll get to that in a second. Zn ions are deposited at the zinc electrode as Zn. Okay. This one is kind of screwing my brain a little bit with the wording of C. So I want to write down A, B, C, D, because that's always what I do when I'm not sure, because I want to eliminate slowly. And then the concentration of... No, we just said that's not true. The concentration does not increase because it's going to be reduced because it's going to go... This is at the cathode, meaning that it's... that we're going to observe the copper residue being formed, right? So we know D is wrong. C, I'm not sure. A and B are very similar. And what we do know is it's going to want to balance charge. So if I'm not mistaken, it's going to go into the positive ions are going to flow into the one with the cathode, which is going to be the copper half cell, right? Well, we already know these two are really similar, meaning that one of them has to be right. So I feel like it has to be in between A and B. But then why is this not? Because is it talking about the formation, like the ions will form that? Because that's not true. Or wait, hold up. I'll deposit at the... Okay. I'm going to go with A. I'm not entirely confident with the answer there, but I'll go with A. Yeah. Okay, so now we get into the reasons why. Why not? So we know cations, yeah. We'll move in the direction of cathode. Yes. So because it's a bouncing charge, right? So we're going to observe the positive ions from the salt bridge move to the cathode to balance the charge. As the positive ions are being used up. I'll just write down, for example, Cu2 plus are being used up. So that's why the B is wrong. So Zn, yeah, okay. My question is just more about the wording of C. Zn2 plus are deposited at the zinc electrode. No, so yeah, it's talking about the formation. It's not going to form that. No. It's undergo oxidation, right? Hold up. Wait. Yeah, it won't, right? Okay. I want to review this. I'm going to ask my teacher. Ask why C is wrong. Because I want to understand that later, personally for myself. Whenever you have stuff that you just don't understand, don't ignore it. Just either you can come back to it at a later date, just note it and make sure that you come back to it, or right on the spot. Right on the spot, Google it or something similar. And then that way you'll know the reason why. So if you're ever presented with that sort of question again, you can get it. Okay, voltaic cell. I'll just eat off screen quickly while reading. Okay, so understanding voltaic cells, should be able to get number one fast. P, voltmeter. Q, salt bridge. Should be jumping at for joy if you ever see that question. Or that type of question. Using section 25, so I need to pull up my data booklet quickly. Okay. So this is 25. Using the activity series, so we have zinc and we have cadmium. So that's going to be CD. CD is higher than, no, Zn higher. So I'm going to write that down quickly. Zn higher than CD. You can't see my screen right now because I blocked it quickly. So that's all we need that for quickly because it said just section 25. State the overall equation of the spontaneous reaction that would occur in this. Okay. So because it's higher up on the activity series, we're going to want this to be oxidized. So we're going to go from our Zn plus, I'll add the stuff in a bit. Hold up. Spontaneous reaction is going to look like this, if I'm not mistaken. We're going to have this be aqueous. It's going to be solid, aqueous, solid. Draw arrows above the apparatus labeled P. So electron flow. We know that our zinc's going to be oxidized. So according to Croa, we're going to have our anode. This is going to be our anode. So our electron flow is going to go from our anode to our cathode. So it's going to go from zinc to cadmium. So I'm just going to sketch whatever the heck they drew quickly. Really quickly, whatever. Let's call that as the drawing. And this is going to be the E flow of electrons from zinc to cadmium. Very cool. Sorry, let me not capitalize that. And then a student is required to make up. Okay, so convert the 200 to dm cubed. So we're going to do 0.2 dm cubed. Multiply that. So we have 0.2 moles of cadmium nitrate. Cadmium nitrate. So we have CD2NO3. Wait. CdNO32. And then the mass of nitrate that must be used. So pull up a periodic table, multiply periodic table. What is the mass of cadmium? Let's see. CD cadmium. If it'll, that's a terrible resolution picture. 0.41 multiplied times 0.2 is going to give me this as my answer. 22.48 grams of cadmium. Well, okay. Never mind. It's going to be cadmium nitrate. So that's how much cadmium. Then we know this is, so 2 times 0.4, 14.01 plus, what is that going to be? 48.96, 96 times 0.4, 38.4. To add these all together, or I'll just do it in my head quickly, or just write it down actually. So 28.08, no, 4 grams, like 28.48 grams. Oh, I forgot to add the extra 38. So 28 plus 38, 28, 38, 66. Let me scroll on to the last question, make sure that I'm correct. No, I am not. That's fine. Happens. So I didn't do the molar mass properly. That's what happened. I messed up, and where did I mess up? It's just because I didn't do the process quickly. I was trying to be lazy. Hold up. Okay, so let's go back to the periodic table. Let's return to it. Man, I'm hungry. Plus 28.02 plus 96. It's all going to be equivalent to, it's looking like 140.043. So it's looking like 236.43 grams. 236.43 multiplied times 247.29. Yeah. So it's molar mass, multiply that by the amount of moles that we have, and we're going to find the mass, which is 47.29 Cool. We know that it's going to go from zinc to cadmium. We established that earlier. Zinc to cadmium from the anode to the cathode. And then let's double check my equation. State symbols are correct. Yeah, Zn, cadmium. Cool. Question 15. Question 15. I'm actually going to take a quick break, so I'll be back. Okay, that took quite a bit, but it happens. Moving on. Oh. Nitrite changes to nitrite. It's just something that you do with your polyatomic ions. So NO3 becomes NO2. This is one. Okay. So we're going to undergo a reduction in oxidation state. So just by looking at it, it's both going to have a negative charge. So I'm already saying C. Yeah. Cool. I think that's very self-explanatory. As soon as I finish this, I'm going to move on to working on essays and stuff because I want to keep cycling through stuff. Yeah, I'm coming. Hold up. No. I'm needing it, please. What are you gonna need it for? Hey, hold on. Bye. Ciao. Yeah, see ya. Keeping the screen faced this way is kind of a pain. Not kind of, it is a pain. Balance equation between sodium and water. Aren't we gonna... Ow. So if we have this, won't we observe something like... And then balance it. It's looking like 2, 2, 2, 2. So it's considered a redox reaction because yes. So this goes from 0, and sodium is that's the first one, right? Okay, so that becomes +1. This one this goes from 0. Well, from +1 to 0. So sodium undergoes a loss of electrons, and hydrogen undergoes a gain of electrons. Sodium undergoes a loss of electrons, indicating that is Leoger. So this is oxidation. Hydrogen undergoes reduction. Teacher's hard. 3 alkali metals that react with waters based on observations. Explain my answer. Arrange the metal in order from weakest oxidation agent. So what I want to do is I want to start off with Leoger. OARA. This is going to be strongest, so it's going to be inverse activity series, if I'm not mistaken. So whichever one is going to... So let's look at our activity series. Let's refer to it. Always going to be table 25. Dang it. Because we have our inverse from here. Right. So our strongest metal is most reactive metal. It's going to be highest on the activity series, most willing to undergo reduction, right? So I would say it's looking like Y, X, W in that order, as Y will be well. Hold up. What's willing to be oxidized? Slow reaction means it's not willing to be oxidized. So wouldn't it be actually more like WXY? WXY as Y is, well, more like is willing or is more reactive. Well, that's the thing. This is where I'm coming into issues with it. Is more reactive. Okay, never mind. It's not the inverse reactivity series. I think it's the same thing as the reactivity series, just flip signs. I think that's what I meant to say. We'll see. We'll see the mark scheme in a second. This is where the answers are kind of sketchy, but more reactive, thus is stronger, reducing or higher on activities. No, yeah, that's what I was thinking. Okay. It's fine, it happens, but so vigorous reaction with water, most reactive. Oh dang. They also messed with the no they didn't. Oh they did. Vigorous, fast, slow. So X Y Oxidizing agent is a substance that oxidizes another substance and itself gets reduced. A more reactive metal loses electrons and gets oxidized more readily. Cool. Question 17. Zinc is a more reactive metal than silver. So zinc is more reactive than silver, so this is a higher reducing agent. Which electrolyte would not be a suitable choice? Okay. Zinc loses electrons. This gains electrons. Maybe chloride because the reduction of chlorine gas. I don't see an issue with the other ones. This is what makes you think? Oh, never mind. I got it right, but not for the right reasons. Okay, need to review this. Ions in the salt bridge must be inert. They should not live with their ions in the solution. And the chloride ions react with the silver. To form silver chloride. Yeah, this is looking like one of those days today where I'm saying this right now, but it might look like I'm actually gonna do it for an hour and 20 minutes and then end. Yesterday, or 2 days ago, I was really into it and I was like, yeah, let's go. But yeah, not today. Cathode reduction. So I was going to flow from anode to cathode. From anode to cathode. So I need to identify which one's being reduced. This is being reduced. So it's going to go from anode to cathode. Yes, so one is correct. That's correct. Silver ions are reduced in the reaction. Yes. Copper anode will become smaller in size as the reaction proceeds. Well, it becomes smaller in size, if I'm not mistaken. But it wouldn't get bigger. So I'm going with A. Okay. Okay, that's good to know that the mass and size will decrease. Didn't know that. Mass and size, the anode decrease over time as it undergoes oxidation. Probably gonna play some Balloons Tower Defense after this for a bit. Just need something to get my mind off school. No, I'll return back later. Okay. Now on to question 19. Using section 25 of the data booklet, state which metal forms the anode in this cell. So Cu is the anode. Why? Because according to Croa, we want our Leo Ra Ger Oa. No. So the one being reduced, so zinc. That's why it didn't sound right to me. Zinc is the anode. State the cell diagram for this cell. What is the cell diagram? Is that the... Yeah, okay, that's what I was thinking it was. One's on the right reduced. Deduce the half equations for the reactions occurring at the negative electrode and the positive electrode in this voltaic cell. The copper become more blue as the non-spontaneous reaction proceeds. Okay. A down cell. Oh, let me write that up here. I actually need to advance this my answer. That's what I was thinking. Oh, no wonder. Question 21. I just desperately need a break. But, okay. Considering the fact that nobody's watching us, I'm going to tilt my computer more towards me. Hello, whoever joined. Sorry, I'm pretty much just gonna end the stream soon. I'm pretty much out of it right now. Yep, they left. Hello, whoever joined. I'm about to stop streaming in a second. Well, not a second. Whenever I finish topic 19, because it's what I've been doing for like the past 2 hours and really want to stop looking at it. So, yeah. Okay, I just went through the Revision Village question bank for topic 9. Pretty cool. Whoa, what? Apparently I missed a question somewhere in here. The mark is complete. So yeah. Went through the thank you very much for watching. I think I'm gonna end the stream now. I really like to relax. It's not gonna turn into one of those days like yesterday or 2 days ago where I just kept going. But either way, thank you very much for watching. I really need to relax. So just getting some stuff done while I'm talking quickly at the end. Getting some stuff charged. And yeah. Okay. I think that's it for today. Well, I'll study more later. I'll see whether or not I would like to stream it, but yeah. Thank you once again for listening. Bye-bye.